Welcome to Mechanical Design Hub. In this explainer, we're diving straight into the engineering mechanics, the physical anatomy, and the rigorous specifications behind transmission shafts. If you're studying machine design or you're just fascinated by what makes industrial machinery tick, you're in the exact right place. We're going to break down the highly engineered backbone of modern industry. Here's our roadmap for today. We're covering the mechanical power, link, shaft anatomy and geometry, managing stress and fatigue, shaft typology and evolution, materials and manufacturing distortions, and finally, the specification workflow. We'll build our understanding progressively, moving from the macro function of power transfer right down to the specific workflows you'll use to design these critical elements. Let's kick things off with Section 1, the mechanical power link, bridging creation and application. Think about a fundamental engineering problem. How does rotational power bridge the gap between creation at the motor and application at the output? You know, we have a power source like an electric motor or an internal combustion engine, and it's generating all this energy. But that rotational energy is basically useless unless it physically reaches another machine component to actually do some work. So how do we get that power from point A to point B efficiently and, most importantly, safely? Well, the elegant solution is the transmission shaft. Power flows directly from the prime mover on one end, right into the shaft. This creates a rotating backbone. It securely supports transmission elements, think gears, pulleys, sprockets, and actively transmits that power, motion, and critical torque right down the line to the output machinery.
Let's establish a formal definition. A transmission shaft is a rotating machine element, fundamentally circular in cross-section, that transmits power, motion, and torque. But here's the crucial takeaway as we get deeper into machine design. A shaft is absolutely not just a spending metal rod. It's a meticulously calculated structural element that has to handle some incredibly complex simultaneous loads.
Moving into Section 2, Shaft Anatomy and Geometry, Engineering the Structure.
Out in the real world, a shaft doesn't just sit there in isolation. It has to seamlessly interact with bearings for support and helical gears to transfer torque. It also needs varying diameters to fit all these components perfectly, all while maintaining total stability under high-speed, really heavy loads.
Because of this, the geometry of a shaft is incredibly intentional. Take a look at how the maximum diameter is always placed right in the dead center. Why? Well, bending moments are typically at their absolute highest right there. That thicker center is what maintains structural integrity and rigidity against the heavy bending loads pushing down from gears or pulleys. So let's lock in the primary structural rules of shaft geometry. First, you center the maximum diameter to resist bending. Second, you precision machine the minimum diameters at the far ends. That's where your bearings go to let the shaft rotate smoothly. And third, right between those varying diameters, you have what we call shoulders. These step transitions act as hard physical stops to precisely position your gears and bearings along the axial length of the shaft.
That brings us to Section 3, Managing Stress and Fatigue, the Invisible Enemy.
When you have these sudden changes in diameter, you run straight into a major engineering conflict: stress concentration. Look at that dangerous red zone on the left. When you leave a sharp 90-degree corner at a diameter step, it creates immense localized stress. Under constant rotation, that is a guaranteed recipe for rapid fatigue failure. The shaft will literally snap. To fix this, designers have to apply a fillet radius, which you can see as those smooth blue curves on the right. That simple rounded corner neutralizes the danger, letting the stress flow smoothly through the transition. It's an absolute engineering necessity.
Okay, let's jump to Section 4, Shaft Typology and Evolution, from line drives to CNC.
It's important to remember that not all shafts do the exact same job. Depending on the specific application and loads, we categorize them into distinct typologies. An axle, for instance, primarily handles bending moments from weight and bearing reactions, usually with zero torque involved, kind of like a standard railway wagon axle. A spindle is a short shaft delivering high-precision, localized power, like the drive shaft on a lathe. Then you have counter shafts and jack shafts. These act as secondary or intermediate spatial bridges inside multi-stage gearboxes, rotating counter to the main shaft to step down speeds.
The application of these shafts has totally transformed over time. Historically, factories relied on group drives. Picture a massive, continuous line shaft running across the ceiling, driving an entire factory floor from one single motor using a crazy network of belts.
But today, modern engineering has completely shifted to individual drives. Having decentralized motors on every single machine offers way better control, safety, and modularity. Those old line shafts are pretty much obsolete.
Next up, Section 5, Materials and Manufacturing Distortions, Metallurgy and Practice.
So, what exactly are these components made of? Material selection always scales directly with your strength requirements. The absolute gold standard for your everyday, ordinary transmission shafts are medium carbon plane steels, often just called machinery steels in the industry. We're talking about grades like 30C8 and 40C8. These give you a really optimal, highly cost-effective balance of machinability and baseline strength for standard mechanical applications.
But plain carbon steel won't cut it for everything. When your design demands extreme hardness, exceptional toughness, inherent corrosion resistance, or you're dealing with a massive diameter where plain steel loses its internal hardness, you have to escalate to premium alloy steels. By adding elements like nickel, chromium, or molybdenum, think grade 16 Mn5 Cr4, you achieve vastly superior properties. It's just going to cost you a bit more upfront.
Now, here is a massive warning for when you actually go to manufacture these. If you use cold-drawn steel, watch out. Cold drawing packs the outer surface with extreme residual stress. If you take that shaft and machine it, say by cutting a slot or a keyway, you suddenly release those trapped stresses unevenly. The result? The shaft will severely warp, bend totally out of alignment, and become a massive headache to fix.
Finally, Section 6, the specification workflow, synthesizing the design.
So how do we bring all these lessons together? You follow a strict 4-step workflow. Step 1, identify the specific role. Are you designing an axle, a spindle, or a high-torque main shaft? Step 2, determine and map out the geometry, making sure your maximum diameters are central for bending loads and that you've got generous fillets on all those shoulders. Step 3, select your material, sticking to medium carbon steel unless alloys are an absolute must. And Step 4, specify the proper manufacturing process. To avoid that nasty warping we just discussed, you'll usually want to specify hot-rolled, turned, ground, and oil-quenched bars.
And throughout this whole process, remember, you aren't just guessing sizes. You'll rely heavily on standardized commercial sizing tiers. These standard sizes range from tiny 5mm shafts all the way up to heavy-duty 200mm structural beasts. Sticking to standard sizes saves a massive amount of money. If your math dictates a size beyond 200mm, standard bars are out, and you're looking at custom forging raw steel billets, which is a whole different ballgame.
We've covered a ton of ground in this explainer, from power flow and geometry to stress concentrations and metallurgy. So I want to leave you with this final thought. Considering the complex interplay of dynamic bending loads, the invisible threat of fatigue stress, and the precise metallurgy required to hold it all together, is a shaft really just a simple piece of metal? Or is it the highly engineered, meticulously calculated backbone of modern industry? Next time you see heavy machinery in motion, take a second to appreciate the unseen engineering embedded in the transmission shaft that makes all that movement possible. Thanks for hanging out with me today at Mechanical Design Hub. Keep learning, keep designing, and I'll catch you in the next one.